Welcome to the mathematics and a new video about low degree polynomials. Yeah, it's about similarity. We will need the golden ratio and a pentagram or a pentagon. And to get more details, we take a look at the content. So first we talk about what is it about, what do we need, and some recalls. And then we discuss basic properties of quadratic polynomials. This will be quite fast, everybody knows it. It's about a turning point and symmetry. We take a look at the average of the zeros, then for similarity. Then we discuss, I call it zeros of tangents, then a nice property orthogonal tangents, and a simple calculator involving parabolas. Then the third point is about similar stuff for the cubic polynomial. We prove the existence of the inflection point. Then we discuss symmetry and similarity. Then also we take a look at the average of the zeros. We take a look at the zeros and tangents. And in the last point for the cubic polynomials, we discuss how we can use the graph of a cubic for basic operations like plus, minus, and so on. The last point is the quartic polynomial or quadratic polynomial. We will discuss in particular quartics with two inflection points, and we discuss also similarity like for quadratic and cubics, and we have also a nice property involving seconds and intersections, and then we get the final. That's what is it about. Okay, so what we want to do is we want to consider a 4-degree polynomial, ax to the power 4 and so on, with two inflection points. And of course we will give necessary and sufficient conditions for this behavior. And for some mysterious reason we will find a specific number. It's the golden ratio, as you can guess. And before we start, I want to discuss similar properties for quadratic and cubics. They're also interesting, I guess, and then maybe it's a kind of motivation how to come up with this stuff. Okay, and we will need beautiful relations, and we will discuss also how we can how to come up with stuff with previous results, and enjoy. Let's start. Now for the requirements, you should know completing the square. I will not go in these kind of details. The quadratic formula you should know. Then basic calculus, you should know the derivative of a polynomial. So how you derive it. Then the product rule is important, and of course the equation of a tangent line through a given point P. It's here. And then we should know that every polynomial over the complex numbers has degree of P zeros. And the audience for whom is this video? It's not for students. So if you study mathematics, then you will be disappointed, I guess. It's not rigor. It's more for laymen or for people who are interested in polynomials. Okay, if you have basic knowledge, then you can follow. If you do not know stuff about completing the square, please make sure you know that. Okay, I will not go through these kind of details. Okay. Alright, let's start with the quadratic polynomials. So, we consider p of x is ax squared plus bx plus c, where a, b, c are real numbers and a is of course not 0, otherwise we would not have a quadratic. Okay? And then there is the existence of the turning point. The x coordinate is minus b over 2a, and the y coordinate you find if you take the x coordinate and evaluate it on p. Okay. Then the symmetry, every quadratic p is symmetric to a line x equals xt, where xt is of course the x coordinate of the turning point. Okay. Yeah, so just make it clear graphically. Yeah, if we have a parabola, then of course here is our turning point, and every parabola is symmetric to an x coordinate of the turning point. Okay, so this means, so this distance is the same as here, and that's for all points. Okay, I'm pretty sure you know that, but just in case. Okay, so we start easy. Then the average of zeros. Yeah, we consider again p of x, ax squared plus bx plus c with two real or complex roots x1 and x2. And if we add both roots and divide by 2, so in other words, the arithmetic mean of the zeros is equal to the x coordinate of the turning point. Yeah, the proof is of course very easy. I leave it to you. Yeah, and we can see this also graphically. Yeah, if we take a look at the graph, yeah, let's consider there is our x-axis. Yeah, because of the symmetry, here this distance is the same as here. Okay. All right. Yeah, and why I show this theorem, we will see that this is also, there is a similar stuff for the cubic also. Okay, so that's why I show this theorem to you. I know you are familiar with that if you know about the quadratic polynomials. So then next we take care of the similarity. And what do I mean by that? I mean by that two functions y equals f of x and y star equals g of x star are similar if there exist mappings x star is phi of x and y star is c of x, such that y star equals g of x star equals psi of f of phi inverse of x star. Okay. Yeah, here this is a little bit cryptic. This is also not the general case. There's a more general case involving matrices. I'll keep it simple, but we will see what this means. Okay, what I mean by that is every parabola is similar to the normal parabola. If you take a general one and you move it and stuff like that, and maybe you yeah, if you shift it and stuff like that, then we get the normal parabola. Okay, and yeah, the theorem 2 says every general quadratic polynomial is similar to y equals x squared, and by definition of similar we have to find two mappings, and yeah, we can do this quite easily. So first, what we do first is, by completing the square, we can find this form a times x minus s squared plus t. Okay, and then we make a coordinate transformation. X star is a times x minus s, and y star is a times y minus t. Then we take the first equation and we solve for x. So we have x is phi inverse of x star, and this is s plus x star over a. Okay, and now we have to be careful. So the first step is we take phi inverse of x star. Okay, remember, phi inverse of x star is s plus x star over a. We put it in p. Alright? Then p of s plus x star over a, we find this equation. A times s plus x star over a minus s squared plus t. And you see that the s and minus s cancel out. And we are left with a times x star over a quantity squared plus t. Now we write in the argument of psi as x star squared over a plus t. Now remember, psi of y is a times y minus t. If we plug that in, we find a times x star squared over a plus t minus t. So t minus t cancels out and a over a cancels out, and what we get is our statement similar to the normal parabola. Okay? So again, what I wrote here is a little bit cryptic. All we need is there exists a coordinate transformation. In this case, it's this one. So we make a coordinate transformation, and therefore every general parabola is similar to the normal parabola. Alright? Okay. Zeros of tangents. Yeah, this is a nice property in my opinion. I dealt with that several times in physics, in electromagnetism, stuff like that in school. Yeah, I think it's worth to talk about it, and it's also for similar statements for cubics and for the quartics. So Theorem 3, for all tangent lines on a quadratic function y equals a times x squared, on x0, the zero of the tangent is x0 over 2. Yeah, the proof is easy. It's a homework for you. The next point I want to talk is orthogonal tangents. So we consider two orthogonal tangent lines on a quadratic p of x. Okay, then the y-coordinate of the intersection point of these two orthogonal tangents is independent of the choice of the tangents. So in other words, the y-coordinate is constant. Okay, so we prove it. The details are homework. So because of the similarity of Theorem 2, we can concentrate on p of x is x squared. And we consider two arbitrary tangent lines t1 and t2 on p, and we calculate the intersection point. And then we use the orthogonality. Okay, so first tangent line is y1 is p prime of x1 times x minus x1 plus p of x1, and of course p prime of x1 is 2 times x1, and the same we do for y2 x2. Okay, now for intersection point we set them equal, then we move around and we get that x is the average of the two x values, yeah, so x is x1 plus x2 over 2. Then to find y, we get x1 times x2, so I leave these details for you. And now, because of the orthogonality, we get minus 1 over 4. And also, this is a homework for you. So make sure you understand this. And this shows that orthogonal tangents, the y coordinate is constant. And this is a pretty nice result in my opinion. And yeah, and thanks to the similarity, please recognize for a general tangent, for a general parabola, we can use the similarity to get the where is it here? Where is it? Yeah. And if you use a general quadratic, the similarity allows us to take care only of the normal parabola. Okay. So if you have a general parabola with the similarity theorem, you can calculate the constant y term. Okay. Yeah, simple calculator. This is also really nice property. Theorem 5, the intersection of a secant through 2 points on a parabola and the y-axis is equal to the negative product of the x values. Okay, what does this mean graphically? This means so if we have a coordinate system like here, and we take a normal parabola, maybe that one, and then we take a secant line, for example this one, then there is an x1, here is x2, and if we multiply them, the product, we get the product exactly here on the positive y-axis, okay? And because this is negative and this is positive, we get the negative product. And so x1 times x2 we find exactly here. And therefore the parabola, the normal parabola, can be used as a simple calculator for multiplication. And we prove this. Yeah, this is quite easy. What do we do first? We multiply out mx minus mx0 plus y0, and this is of the form mx plus b, and we want to find b. Okay, so we move around stuff in this equation. We find b is y minus mx. Then we take, for example, p1, so y1 minus m times x1, and m is from the second line y1 minus y0 over x1 minus x0. Alright, what can we do here? y1 is x1 squared and y0 is x0 squared. We use the binomial, so the square of the difference of a square formula, and we get immediately the negative product. Okay, so pause the video and make sure you understand all the details. Pretty nice result in my opinion, and we will see that we have something similar also for cubics. That's why I show this. And yeah, that's the end of the properties for our quadratic polynomial. We come to the properties of cubic polynomials. So we consider p of x is a times x cubed plus bx squared plus cx plus d, a, b, c, d real, and a is not 0. Otherwise we would have a quadratic. Okay? So existence of inflection point. For all cubics there exists exactly one inflection point xi. yeah, the proof is we find first the second derivative of p. This is 6a times x plus 2b. So the necessary condition for an inflection point is p. So the second derivative is 0, so we get xi is minus b over 3a. And this value exists since a is not 0. Okay, that's why it exists. So the sufficient condition, the third derivative is not 0, and we find the third derivative is 6 times a. This value is constant, and it's also not 0 since a is not 0, so the sufficient condition is also satisfied. Therefore, we have exactly one inflection point. Now the symmetry is also very interesting. All cubics are point symmetric to its inflection point. Yeah, how to prove this? We prove this, we shift our general cubic, we shift the coordinate system to the inflection point, and we show that all exponents of the new equation are all odd, and therefore it's point symmetric. Okay. There is a download link in the video description. I will not go through all the details of the proof. If you want to see it detailed, please download the document. So we take an inflection point, these are the coordinates. Then we define a new g of x. It's f of x I plus x minus yi. So we move the new coordinate system into the inflection point. Then we calculate a little bit. It's not so difficult. We have to take care of all the signs and all the exponents. And what we get at the end is a cubic a times x cubed plus some coefficient times x. So there are only odd exponents, and therefore the condition for point symmetry is satisfied, and therefore all cubics are point symmetric. Okay, so for the details, please download the document. Yeah, and also we can try to talk about similarity also for the cubics. Okay, so we know all cubics are point symmetric to its inflection point. So maybe it makes sense to find also some similarity properties. And this is a homework for you. Find a condition for the non-existence of a local maximum and minimum. So what I mean by that, if there exists a local maximum and minimum, then there is a certain equation, and if there are no local maximum and minimum over the reals, then there is a specific type of equation. And what I want you to do is find a condition for the existence and the non-existence of a local maximum and minimum without using calculus, and write down a statement like all p of x are similar to one of following cubics, blah blah blah. So q of x is something if the relation for coefficients. Okay, you can try that. Yeah, after similarity, we can take a look at the average of the zeros, like for the quadratic polynomials, and this is also very interesting. The arithmetic mean of the three real or complex zeros x1 up to x3 is equal to the inflection point xi. This is a very, very beautiful result in my opinion, and the proof is really easy. We use Vieta's theorem, and we immediately have this property. Okay, you can try to prove this result without using Vieta if you like. For my opinion, using Vieta's theorem is very elegant, and statement is immediately proven. A little homework for you: the arithmetic mean of the real or complex zeros of the derivative of a cubic is also equal to the inflection point. This is my homework for you. And there is a more general case. The arithmetic means of the zeros of a polynomial p of degree n is equal to the arithmetic means of the zeros of its derivatives. P, so the first, the second, up to the nth derivative. Okay? This is also a very beautiful result. And to prove, you just have to generalize this proof from Theorem 8. Okay, so download the document and think about that. It's not so difficult, and it's a very nice property in my opinion. Yeah, this is one of my favorite statements, the average of zeros and tangents, Theorem 9. Let x1, x2, x3 be real or complex zeros of a cubic. Then p prime, so the derivative evaluated at x1 plus x2 over 2 times x3 minus x1 plus x2 over 2 plus p of x1 plus x2 over 2 is 0 for all cyclic permutations of the zeros. Yeah, what does this tell us? So we first prove it. I leave this also for you. I'll show you a more elegant proof in a minute. But if you want to prove it naively, yeah, you take q of x, then you take the derivative, you evaluate them at the average of x1 and x2, and using Vieta's theorem, on some point you should get 0. Okay, and it's not difficult. It's a little bit of writing down, and be careful that you do not miss a sign or something like that. Please try it. It's a nice exercise in my opinion. And before we prove it in a more elegant way, how to come up with stuff, something like this, and you may wonder what is this equation telling us. Yeah, take some weird combination of derivative and cubic and combine them with a combination of the zeros, and you get 0. Yeah, what is this telling us? And like I said, if you try it this Vieta's way, you may say, is there a more elegant way? And we will come to that in a minute. First, I want to show you what this equation is telling us. I draw a picture. So we take a cubic with 3 zeros, for example, like that, and then we take our coordinate system. It's maybe here, it's not so important. So what is this telling us? Here is x1, x2, x3, okay? And this equation is telling you, and if you go and if you take a tangent through x3 but not this one, if you take this tangent like here, this one, then this point here, this point is x1 plus x2 over 2. This is what the equation tells us. In other words, the 0 of the tangent through x1 plus x2 over 2, the 0 exactly intersects at the last 0. Okay? Please make sure you see that on this equation. This is a really beautiful result, and what I want to say is this works also if you take these two and you take the so if you take x1 and x3 and to take over 2, and to take the tangent you will hit x2. Okay, so it works for all combinations involving x1, x2, x3. Okay, what a nice property. And like I said, if you try to prove it with Vieta's theorem, it's a little bit hard because so many terms, and yeah, you have to take care about the signs. We prove it more elegant, and like I said, there is a more elegant way. Yeah, I want to make a recall. The product rule. No, we forget about this for a second. The product rule, uv prime is u prime v plus uv prime. Okay, and also if we have 3 factors, uv prime is u prime yv plus uv prime y plus uyv prime w prime. Okay, pardon for the misspelling. And we write this in another form. Make sure these 2 forms are equal. Okay, so this form is equal to that form, and this form is equal to that form. So what is here more useful? Here is more useful if we take the form p of x is a times x minus x1 times x minus x2 times x minus x3 instead of this form. We find immediately this result. Immediately. We try to calculate the derivative, and on that point we get immediately this form, and now we multiply by the denominator and move stuff and move things around. We get immediately to this result. Okay, and this is in my opinion a very elegant way. Please take your time for the details. Please check it out. It's really beautiful in my opinion. The next point are the basic operation using a depressed cubic. And first we have to define what is a depressed cubic. A cubic is called depressed if it has the form x cubed plus px plus q, pq are real, or in other words, there is no quadratic term. And there are some nice properties of a depressed cubic. Because of Vieta, we know immediately the sum of the 3 zeros is 0. Please check, so please make sure you understand this. And we know also the inflection point has coordinates 0, q. This is also what we know immediately. This is also very beautiful. Okay, also here, please make sure you understand these 2 properties. And we have a nice theorem 3. Let p of x be a depressed cubic, and let x1, x2, x3 be the 3 roots of p of x. Let t of x be nx plus s such that p of x equals t of x gives 3 real solutions, t1, smaller t2, smaller t3. Then t1 plus t2 is minus t3. Okay, what is going on here? So first, so imagine we have a depressed cubic. I hope I can do it right now. I think this can be a depressed cubic. So just so let this be a depressed cubic. If we take a secant with 3 intersection points like this, okay, so 1 intersection point here, 1 here, and 1 here, then our theorem says that this point plus this point equals negative this value. Okay, so this is what our statement is telling you. Okay, and the proof is really easy. I don't want to go to the details. The secret is of course this property. All you need is this property, and then you immediately get this result. As a homework for you, I have a beautiful homework. So consider T1 smaller, T2 smaller, T3 as in Theorem 10. Give an expression for T1 times T2 times T3 in terms of P, Q, M, and S. The second homework, use a bijective scaling to multiply or divide. What I mean by that is, instead of plus, I want a multiplication. So you have to find a scaling to multiply, and which special cases of multiplication or division do we get for T1 equals T2 smaller T3. Okay. And the third one, let P of x and T of x as given in Theorem 10. Find all pairs MS such that P of x equals k times P of x minus T of x for some real k. Alright. Now, the properties of a quartic polynomial. We consider P of x equals a x to the power of 4 plus bx cubed and so on, where a up to e are real and a not zero, with two inflection points. Okay, so we consider only quartics with two inflection points, and of course our first theorem is a sufficient and necessary condition for a quartic having two inflection points. So a quartic has exact two inflection points if and only if a times ac is less than 3 times b squared. And the proof is simple. We take a look at the second derivative. It's 12ax squared plus 6bx plus 2c. Then we consider the discriminant of the quadratic polynomial. It's this one here, and then the result follows immediately. Okay. Theorem 12. 12 is dealing with there is no quartic with exactly one inflection point. So in other words, a quartic has 0 or 2 inflection points, but not one. I leave this proof for you as a homework. Theorem 13, another necessary and sufficient condition for a quartic having two inflection points is following. So the second derivative evaluated at minus b over 4a and the leading coefficient a have opposite signs. So leading coefficient a is this one, okay? And the second derivative evaluated at minus b over 4a, this value and this value, they have opposite signs, and then if and only if there are two inflection points. This is a very nice property in my opinion. We prove this, and the proof, you see, it's quite simple. It's a homework, and it follows from Theorem 11. Okay, so take care of this discriminant. So you will use this equation, you will use this inequality, and if you move things around in a helpful way, you get this result immediately. Okay, nice. Similarity. We have also a similarity for quartics, and this is very interesting in my opinion. Every quartic with two inflection points is similar to a quartic x to the power 4 plus w x squared, where w is negative. Very interesting in my opinion, and we prove this also yeah, with a coordinate transformation, and this goes like follows. We define x0 such that the third derivative of x0 is 0. In other words, x0 is minus b over 4a. Okay? Then we define a k via the square root of second derivative evaluated at x0 over 2 times a times w, where w is negative. And by theorem 13, we know this is positive. Okay, so k is positive, it exists, it's real and not imaginary. And yeah, we will need this k for the polynomial q. Okay, we will see how we will use this. And now we consider a coordinate transformation via what? X bar is kx plus x0, and y bar is a times k to the power 4 times y plus p prime of x0 times kx plus p of x0. This is yeah, I wrote here general case. Maybe you remember by the definition of similarity, I told you there's a more general definition using matrices, and here is the coordinate form. You can try to write that in form of a matrix. Okay, and if you plug in all the stuff, I leave these details for you, you will get the desired result. Okay. Yes, how I'm also here how to come up with stuff like this. This transformation is a scaling transformation. Yeah, we have a scaling factor k in x direction, and a times k to the power 4. There is some absolute values in the y direction, and yeah, if a is less than 0, we have a reflection about the x-axis. And we have also a shear in the y direction and a translation. So the translation you find here in x0, p of x0. Here's the scaling, kx and ak to the power 4. And there is the shear, this vector k. Okay? Nice. Yeah, and theorem 14 allows us to explore properties for this very nice form of a quartic, and then via similarity we have a class of quartics with nice properties. Alright, so seconds and intersections. Let q of x be x to the power 4 minus w squared x squared be a quartic, and s plus minus of x equals plus minus mx the seconds through a minimum of q of x and the origin. Then q of x equals plus minus s of x has 4 distinct solutions each. So what I mean by that, so q of x equals plus mx and q of x equals minus mx. Each of these equations has 4 distinct solutions. Okay. I will not show a picture to you. Please make sure you find this picture and make clear visually why this is true, and we can calculate these 4 distinct solutions very easily. I give a short proof. You can go through all the details. So first we show the existence of the 4 solutions. Because of the symmetry, we can concentrate on, for example, s plus. Then q of x, we can factorize q of x easily, and then we can differentiate q of x to find maximum and minimum values. And also using polynomial long division, we get easily a positive discriminant for the remaining quadratic polynomials, so we have 4 solutions. Okay, but I leave the details for you. And all in all, we have 6 distinct intersections and 2 intersections through the origin. Okay, so all in all we have 8, 4 for each equation, 2 of them they fall together, and 6 of them are distinct. Homework: calculate all coordinates of all intersection points. And I have done this for you. If I haven't done a mistake, it should be, yeah, this coordinates x1, y1, x2, y2, x3, and x4, and so on. And please, yeah, here it's written an 8 solutions. Here we have only 4. Remember, the solution is double, and the other 3s, they what do you want to say? Yeah, you find them through reflection. Okay, and what I want to say here also is, for example, y1 can be written as w to the power 4 over 4 times phi, where phi is the golden ratio. And another homework for you is express the coordinates with odd indices in terms of the golden ratio. Nice homework. And the final is, there is a point P5 such that the polygon P1, P2, P3, P4, P5 is a regular pentagon, and the points P1 up to P4 are exactly these points here. Okay, P1, P2, P3, P4, and yeah, they form a regular pentagon. Proof is homework. A, give a non-constructive proof for the existence of P5, and B, give a constructive proof by calculating the coordinates, of course. And another homework before we end, by Theorem 14, all quartic with 2 inflection points are similar. Use the coordinate transformation to find the coordinates of the pentagon of an arbitrary quartic with 2 inflection points. Okay, and yeah, this is the end, and one thing is missing, more or less. I leave that for a small secret. I do not know when I will show this. It's not so important. I plan to do it, but I'm not so good in animation stuff. So first I have to improve my animation skills, and then maybe I can show you the missing thing. Yeah, I wanted to show the last proof of Theorem 9. This was the Vieta's theorem. I wanted to make an animation using Vieta's theorem, but my animation skills are not so good. So just to recall what we are talking about, the Theorem 9, it said it was this equation. Okay, maybe I will make the animation in the future when I improved my skills. Yeah. So thanks for watching, and I hope it was interesting for you. See you next time. Bye bye.